This is section 10.6, Trigonometric Equations and Inequalities, part 2. All right, so this is a continuation of the ideas presented in the last section. And so we're just going to start out with examples because it's the same basic principles. But this time we're going to see different things cropping up. Like in this one, we have different angles. They're both cosine, but one's cosine of 2x, the other one is cosine of x. And if those don't agree, we can't, on the face of it, solve this equation by getting equal to 0 and factoring or something. So let's talk about what we can do. If we have different angles, different arguments of a trig function, like 2x and x are different angles, we're going to have to rewrite so that they're both the same angle, the same argument after cosine. So this is going to involve using trig identities, more so than we did in the last section. So cosine of 2x, there are 3 versions of that one. Which one would be the best for this situation? Well, because there's a cosine of x on the other side, we'd really like for our identity to take cosine of 2x into being cosine of x. So looking at those 3 identities, the one that's going to serve our purpose is the one that is 2 cosine squared x minus 1. That's the one we're going to want to use. Okay, so this is now quadratic. So we get equal to 0 by subtracting cosine of x from both sides. We then hope that it will factor. Since 2 is prime, the only way I can get 2 cosine squared x is to have 2 cosine x times cosine of x. The only way I can get negative 1 is 1 times negative 1. So I know there'll be a 1 in both of these places. One of them is positive, the other is negative. So which way will it go so that we end up with negative 1 cosine x? Well, if it's negative 2 cosine x plus 1x, that works. So if this product equals 0, that means that either cosine of x will equal negative 1/2, or cosine of x will equal 1. Okay? Excuse me. So, thinking about cosine, since it's x over r, cosine will have a negative 1 over positive 2 at 2 places. Whoops, drawing the wrong angle. It'll be negative 1 for x and r equals 2 at that place, and also at that place. Okay, so the reference angle for both of these, this angle and this angle, being across from the long leg, the square root of 3 leg, that means that that's a 60-degree angle. Oh, but wait a minute, we're in radians because it says 0 to 2 pi. So that is pi over 3 in size. So let's see. What is that angle if the reference angle is pi over 3? Pi over 3 is correct. Okay. Or then what's this angle? Starts here and goes all the way around to there. 4 pi over 3 is correct. And that's all of them between 0 and 2 pi that has cosine of an angle equals -1/2. And then where does cosine of x equal +1? If you recall, that's where we use the unit circle because it's a special quadrantal answer. And if r is 1, that means that the cosine of theta is the x-coordinate, and the sine of theta is the y-coordinate, because x over 1 would be x, y over 1 would be x. So if it's a unit circle, that's really handy. And I want a place where cosine of theta equals 1. The only place that happens is right there, and that's angle 0. Okay? So those are your three solutions. Since we didn't square both sides or divide both sides by a variable, we do not have to worry about checking for extraneous solutions. It never hurts to check your answers if you want to, but it's not required if you've not made any mistakes. All of these answers should be good. You may notice that I wrote them in ascending order, mostly because that's what you'll see in the book. So if you write them in ascending order, it's easier for you to check, especially if the list is long. If there are 16 answers or something, if they're in the same order, it's way easier to determine if you're going to be on the right track or not. Okay, so next problem. We're going to encounter an inequality of the same basic idea as the equation we just did. So if we had started with this inequality, I would have done all the work above anyway. I would have set that to be an equal sign, solved for x, and done the number line analysis. Okay? So to do this inequality, having solved for the numbers that are important, we are going to use 0 itself, which is actually the beginning of the domain of possible things, 2 pi over 3. So maybe it's a good idea that I wrote these in ascending order. Makes writing them in the correct order on the number line easier. Maybe that's another reason to do it. And then, of course, we're stopping at 2 pi. Okay? So, what we're going to do for this number line analysis, to do it correctly, we really need to compare to 0. So we really want to do this inequality. So what we're going to do is substitute in test numbers into this expression, or if you wanted to substitute it into one of these up here, you could instead. It won't really matter. And tell if the answer is positive or negative. Okay? So let's pick a number that's between 0 and 2 pi over 3, like pi over 2. I'm actually going to write this one out because it's more complicated than some of the others we've done. So cosine of 2 times pi over 2 minus cosine of pi over 2. Trying to see if that's a positive or a negative answer. 2 times pi over 2 is pi. Cosine of pi is -1. Minus cosine of pi over 2 is 0. And of course that is a negative answer. So between 0 and 2 pi over 3, that's negative. All right. Now between 2 pi over 3 and 4 pi over 3, I'm going to use pi. So I'm going to substitute into that expression cosine of 2 times pi minus cosine of pi. Cosine of 2 pi, which is coterminal with 0, is 1, minus cosine of pi is -1. Of course, that's 2, and that's a positive result. So we put a positive here. Okay, something between 4 pi over 3 and 2 pi. Let's use 3 pi over 2. 3 pi over 2. So cosine of 2 times 3 pi over 2 minus cosine of 3 pi over 2. 2 times 3 pi over 2 is 3 pi. 3 pi is coterminal with pi, so the cosine of that is -1. Cosine of 3 pi is -1, minus cosine of 3 pi over 2 is 0. So that is a negative result. And I did forget, I'll be honest, that I sometimes do this. These are the places where we got equal to 0. And that's important because we're looking for where it's negative, and it's not negative at 0 because it's actually equal to 0 there. So it's kind of important that I have that dot there. It's like, oh yeah, that's where it's equal to 0, and I'm looking for where it's less than 0. So our answer is on the interval starting with 0, because remember we're looking for where it's less than 0, so we're looking for the negatives. So 0 to 2 pi over 3, not including that because it's just strictly less than 0, and then union 4 pi over 3 to 2 pi. Okay, that's that one. Now, what if it had been cosine of 2x greater than cosine of x? Well, the neat thing is if you're doing both of these inequalities, you can borrow the equality work from the first thing we did to find the numbers that go on the number line analysis. Then we can use the number line analysis that we just did to answer this question. So there's actually no more work involved in finding greater than 0. Just look at your number line analysis, look for the plus sign, and it has positive answers on the interval from 2 pi over 3 to 4 pi over 3, and we're done. So actually, the further you go into this, if you end up doing equals, greater than, and less than, by the time you do the last inequality, you've done all the work. You just have to record the answer, and that makes it pretty nice, pretty easy. Okay, so let's do this one. 4 sine of x cosine of x equals square root of 3. And again, this is over the interval 0 to 2 pi. Okay, so the mixture of trig functions in this one bothers me. It has both sine and cosine. I'm not going to be able to get it equal to 0 and then factor to separate the sine from the cosine. That's just not going to happen. Squaring both sides doesn't make it any better because you'll just make it a little bit harder than you need to. So what I'm going to suggest you do is make sure you really know all of the identities that we did, and realize that 4 could be rewritten as 2 times 2. And by my separating the factors of 4 into 2 times 2, like I did, do you see what I did? Yes, that's an identity. 2 sine x cosine x is the same thing as sine of 2x. So you're going to have to look for those identities. Sometimes they're somewhat obscured and hidden from you. You're going to have to look for them for this to work. So product of sine times cosine with the same angle, I'm looking for the sine of a double angle. Okay, so isolating the trig function means I'll divide both sides by 2. Okay. Then I'm going to go looking for when the sine of something is square root of 3 over 2. I'm thinking that means that since sine is y over r, that means I want the y to be square root of 3 and the r too. That can happen in the first quadrant. It can also happen in the second quadrant. And of course, the reference angle is the same for both. And what is that reference angle? We're in radians. It's pi over 3. Okay, so I'm going to suggest, especially if you have a sine of a 2x, 3x, 4x, that you actually find all answers, because you never know what you might need to solve this. So I'm going to actually write all answers to start with, and then I'll find the ones of those that are between 0 and 2 pi. So when our angle 2x is equal to, let's see, in the first quadrant, the reference angle pi over 3 is the angle. That angle is pi over 3. So it's pi over 3 plus all coterminal angles would be plus 2 pi n, or the argument of sine 2x is equal to, and what is the angle in the second quadrant with reference angle pi over 3? That's 2 pi over 3. And then add 2 pi n to that to get all coterminal answers. And then to solve for x, finally, we're going to divide everything by 2. So that's going to become pi over 6 plus pi n. And solving the second equation for x is going to give me pi over 3 when I divide by 2 plus pi n. Okay, so let's start making a list of good answers, starting with our pi over 6 basic angle as a good answer. If I add pi to that, so if I let let n be 1, pi over 6 plus pi is 7 pi over 6, and that's still less than 2 pi. In terms of sixths of pi, 2 pi is 12 pi over 6, so I don't want to exceed 12 pi over 6 in this first vein. So if I add pi, which is 6 pi over 6 to that, that's 13 pi over 6, which is too big. So we're actually done with the first set. Now, I want you to pay attention to this. Had I not put the plus 2 pi in, you would have thought the only answer was the pi over 3. You would have gotten pi over 6, but you would have totally missed the 7 pi over 6. That's why I say start with all answers when the argument isn't just plain x, so that when you get x by itself, you actually can find all of the relevant answers. Okay, so for x equals pi over 3 plus pi n, the base angle pi over 3, of course, is between 0 and 2 pi, so it's good. I'm going to add pi to that. Pi over 3 plus pi is 4 pi over 3. And if I add pi to that, that's 7 pi over 3, which is too big. 2 pi is 6 pi over 3, and 7 pi over 3 is too big. So that's a full set of all of my answers for this equation. And so the solution set contains, and a lot of times I'll just write them, especially if there are only 4, I'll write them in the order I found them. But keep in mind the book may very well put them in ascending order. So if you have 4, you need to be able to look and see if you have the same 4, perhaps in a different order from how they've written them, to check your answer. Okay? Okay, let's see. Let's do another one. Tangent of 3x is equal, oh, I'm sorry. I didn't read it carefully. Tangent of 3x plus secant of 3x equals 2 over the interval 0 to 2 pi. All right, so the fact that I have tangent and secant in the same problem, we saw one kind of like this earlier. The connection between tangent and secant is a squared relationship through that Pythagorean identity. So I'm going to want to square both sides. I don't want to square it yet, though. I need for one of these two to be by itself. This time I'm going to make it secant that's by itself. I don't know what I did last time anymore, but this is going to be my choice. Actually, I think I made it secant last time too. Oh well. Doesn't really matter. Just pick one. So once you've gotten one of the trig functions by itself, square both sides of the equation. And what special note should I make to myself about this process of squaring both sides? Yeah, I might be creating extraneous solutions. Absolutely right. So that means we're going to have to remember to check all solutions. Some of them may be extraneous. Okay, so we get secant squared of 3x. We get 4 minus 4 tangent of 3x plus tangent squared of 3x. Again, the one that I'm going to go with is the one that has the linear term, because I have secant squared and tangent squared, but it's tangent that's the linear term, so that's what we're going to go to. So in case you don't have these memorized, I think I admitted to you once before that I didn't memorize these. Alternative one, I memorized this one. And if I want to get a secant out of it, I'll have to divide 1 by cosine. So I'm going to divide everything by cosine squared, which will give me tangent squared theta plus 1 equals secant squared theta. And so secant squared is going to be replaced by tangent squared of the angle in this problem is 3x plus 1. And luckily for us, it is quadratic, at least at this stage, but if I subtract tangent squared of 3x from both sides to try to get everything equal to 0, the tangent squares disappear. They cancel each other out, and I get this. And now, since this is a linear tangent problem, we're going to isolate tangent of 3x. So I'm going to subtract 4 from both sides. And divide both sides by -4. Okay. Then I'm going to get 3x by itself, I'll need to take the tangent inverse of both sides, keeping in mind that the period of tangent is pi. So to get all answers, I'll need to take that answer and add pi n. And then to get x, I'll have to divide by 3. So that'll become 1/3 tangent inverse of 3/4 plus pi over 3 times n. All right, so since 3/4 is not one of our tangent answers that we're used to seeing. That means that we're going to need to go into the calculator and start typing these in. So make sure I'm in radian mode. I am. So I'll have 1/3 tangent inverse of 3/4, and I'll hit enter, and that answer is 0.214, etc. I'm going to write more digits just so you know what it was in my calculator. And I'm going to store that answer because I might very well need it. So I've got it stored. Plus pi over 3 n. So my first answer is definitely between 0 and 2 pi, so I'm happy with this one. Okay, the next one, I would make n 1, so add pi over 3 to that. And that's 1.26. I'm going to write 2, but you should look at your calculator. It's 1.261699792, etc. So if you're not seeing those particular numbers, you've messed up something. So you need to fix that so that you can get, let me write these out. I'm going to write them out down here below in a little bit more detail. 261699792, etc. Okay. And I might want to store that too. So I'm going to store that in a second memory place. And how far am I going? To 2 pi, right? Okay. So I need to now let n be 2. So I'm typing that in. And I get 2.309. And what I'm seeing there is 2.30889547, etc. Okay. Now do the same thing again. And you should get 3.356, and more of those digits are 3.356093002, etc. Folks, we just passed pi. 3.14 is pi. We're supposed to go all the way to 2 pi, so it looks like we're going to have a long list here. So buckle down, we've got a lot of stuff here. Okay, so get the next one. That rounds to 4.403. I'm going to read them now so that you can compare instead of writing them down. Because if you got the first 3 that I wrote down correctly, all those digits, I'm assuming you know how to do it. So this is actually 4.403299057, etc. Okay, do the process again. I got 5.450. So what I see is 5.450488126, etc. We're still not to 2 pi because that's 6.28. So let's try again and see if it gets past that. We will see. 6.497 is the next one I see. 6.498, let's say. And that's bigger than 2 pi. Remember, pi is 3.14, so 2 pi is 6.28. This is too big. And forget that comma. And those are our candidates. Now, did you remember that we have to check all of those? That's why I wanted you to store them into memory. So, one at a time, we're going to substitute them into the original problem. So tangent of 3 times the candidate plus secant of 3 times our candidate, and ask ourselves if we get 2 or not 2. We're looking for the ones that give us 2. One thing I might say is that when you're typing this, the tangent shouldn't be a problem. Tangent of 3 times your candidate. For secant, don't forget there is no secant button, and you're going to have to type 1 divided by the cosine of 3 times the candidate. Okay, so why don't you pause the recording and see which of these are valid and which are invalid. So pause the recording and see which ones are good. Okay, so in my check of these, I got 0.215 was good. 1.262 was extraneous. 2.309 was good. 3.356 was extraneous. And it looks like they alternate good, bad, good, bad. Don't assume that that's true. Don't make any assumptions like that, because it's sure as shooting you're going to do that, and then the next time it won't work that way. Actually, this time it does, but this is good and this one's extraneous. But please don't make assumptions about any answers you found based on patterns like that that are unsubstantiated. You do really need to check them all. So our solution set contains 0.215, 2.309, and 4.403. Okay, that was a pretty intense problem. Hopefully you were able to follow everything, and that if you have one like this, you can use this as a guide and then eventually become independent of having to look at this as an example. You can just do it all by yourself. Hopefully that's soon. All right, next one. 2 times sine of x over 2 equals 1. Okay, so this already has just one trig function in it. It's not quadratic, so my goal would be to get the trig function by itself. So I'm going to divide both sides by 2. And then I'm going to think, where will I get sine being 1/2? Since sine is y over r, it will certainly happen right here. It will also happen in the second quadrant right there. And as always, those two reference angles are the same. 30 degrees, or pi over 6. Let's look at the directions to see which one of those it should be. From 0 to 2 pi. Okay, so pi over 6 is the version of that we want. So the pink angle is actually the pi over 6. So x over 2, the argument of sine, is equal to pi over 6, and then everything coterminal with it, plus 2 pi n. Remember, when it's not plain x, even if you're just supposed to find the ones between 0 and 2 pi, you really should write that anyway, because it's just a safety net to make sure you capture everything. Or, and then the green one, this angle, is 5 pi over 6, so x over 2 is equal to 5 pi over 6 plus 2 pi n, so and all coterminal angles. 5 pi over 6 and all coterminal angles looks like that. And then to solve for x, multiply both sides by 2. So 2 pi over 6 reduces to pi over 3 plus 4 pi n. And this one becomes x equals 5 pi over 3 plus 4 pi n. And because I have you doing all solutions at the outset, this is actually the answer for part B. I've already done that. And then we'll just have to find the answers between 0 and 2 pi for the A part. So don't be surprised if I do the B part first. So pi over 3 plus 4 pi n and 5 pi over 3 plus 4 pi n. And normally we would probably see someone write comma where n is any integer, but remember I said we're going to make that assumption that it is, and we can stop right there. Okay, so for part A, to get all the answers between 0 and 2 pi, our basic angle of pi over 3 is good. If I add 4 pi to that, it's going to go well beyond 2 pi, so that's the only answer I get from that. And then 5 pi over 3 is good. Adding 4 pi to that takes me well beyond 2 pi, so those are the only two answers we get in the interval from 0 to 2 pi, namely pi over 3 and 5 pi over 3. Okay. Now, they're wanting us to now do 2 sine of x over 2 minus 1 greater than 0. And if you think about it, the equation we just solved was where if I had subtracted 1 at the outset on that problem to compare it to 0, it would have been 2 sine of x over 2 minus 1 equals 0. So we're talking about the same idea as the one we just did. So recall, if I started with the inequality, I would then go and find where it's equal to, and this is from 0 to 2 pi, so we'd end up with pi over 3 and 5 pi over 3 as our numbers to put on our number line analysis. So let's go ahead and do that. Pi over 3 and 5 pi over 3. Oh, and is this function ever going to give us a d/e? It doesn't exist. Is there any number you can't take the sign of? No, it's all real numbers can be used in this function. So in this particular example, we don't have to worry about anything where it doesn't exist. And because I got both of these from thinking of them as equal to 0, I'm going to put solid dots. Okay, then I'm going to do substitutions into this expression. So 2 sine of, see, for our first interval, something between 0 and pi over 3. How about pi over 6? No. Yeah, I guess I'll have to do something like that. I'm afraid I'm going to have to go to a calculator, because you realize that I'm going to take my angle and divide it by 2 and then subtract 1. And I don't know an exact answer right off the top of my head for sine of pi over 12. So I'm definitely going to pick up my calculator and type that in. So 2 times sine of pi divided by 12, subtract 1, I got negative 0.48 something, so that's a negative answer. and so I put a negative here. So between pi over 3 and 5 pi over 3, I think I'll use pi. It's good enough. So this will be 2 times sine of pi divided by 2 minus 1. The sine of pi over 2 is 1. 2 times 1 minus 1 is a positive answer. So put a plus sign here. Then something bigger than 5 pi over 3. How about 11 pi over 6? Oops, wrong color. 2 times sine of 11 pi over 6 divided by 2 minus 1 is the same thing as 2 sine of 11 pi over 12 minus 1. Type that in my calculator. I get negative 0.48 something or other, so that's a negative answer. I'll put a minus sign here. Okay, now we're ready to, after having done the number line analysis, we're ready to find out where does this have positive answers. And looking at the number line analysis, these are greater than 0 on the interval pi over 3 to 5 pi over 3. Okay. This one, yeah, let's go ahead and talk about it. I'm afraid this one will actually require a pretty decent calculator to do, and that may not be something you have, is a graphing calculator. So some of this may be things that I just need to tell you what would happen, and we'll go with it from there. So anyway, a basic component of music is a pure tone. The graph in the figure models the sinusoidal pressure Y equals P in pounds per square foot from a pure tone at time x equals t in seconds. I hope I provided that graph for you. I'm not going to do it justice, I'm sure, but it looks something like this. Of course, I'm not showing you the scale. I'm just trying to mimic what you should see there. And they do lots of these. I'm going to stop drawing it because it's getting worse. My very first period looked pretty good, and then after that it looks pretty sloppy. So hopefully I did provide you the graph to look at for this one. So let's get to the questions. The frequency of a pure tone is often measured in hertz. So frequency in hertz, so the units. A hertz is 1 cycle per second. So 1 hertz is 1 cycle per second, and is abbreviated capital H, lowercase c. What is the frequency f of the pure tone in the graph? Well, if I provided this graph, then you can look at the top where it says what the equation is, and you couldn't have done this without the equation. So if you can't see the graph, I'm going to have to tell you that this equation is 0.004 sine of 300 pi x. 300 pi x. Okay, so that's the model for this pink curve that I've graphed. And the question is, what is the frequency of the pure tone in the graph? What is the frequency? Okay, well, let's, since it's number of cycles per second, we're going to need to know how long one cycle is, right? Does that make sense to you? So the period of this is 2 pi divided by the absolute value of b, which is 300 pi. The absolute value of a positive thing is itself. So the period is 1 over 150. Okay, that's the length of the period. And that's in seconds. So that means that we're getting one cycle, one period, one cycle of the same thing. One cycle every 1 over 150 seconds. So what's the frequency in hertz? Well, that's how many cycles we get per second. So we're getting one cycle for every 1/150th of a second. So this is the frequency that we're getting here. And if you do that arithmetic, that's 150 cycles per second, or in other words, 150 hertz. Okay, and I think I said this earlier, in physics it's a good thing to know that the period and the frequency are reciprocals of each other. The period was 1 over 150, the reciprocal of that is 150. So just saying that's something that you might want to know, because it sure helps keep things straight if you know some of those little facts. Makes it easier to solve things. Okay, the time for a tone to produce one complete cycle is called the period. Well, duh, we already knew that. Approximate the period t in seconds of the pure tone. Okay, so, well, we've already found the period. They want us to call the period t. So the period, which they're having us call t, was 1 over 150. And that's in seconds. And they ask us to approximate it, so they're wanting us to give a decimal answer for that when they say approximate it. So 1 divided by 150 is about 0.00, and then 6 repeating is what it actually is. So that would round to, they didn't tell us how to round, did they? No. So we're going to round to 3 decimal places and call that 0.007. It really is 006 repeating, but you can write that down if you want to. That's exactly what it is. So the period is approximately 0.007 seconds, more exactly 0.006 repeating seconds. Okay, so let's look at part C. An equation for the graph is what I gave you earlier. Estimate all solutions to the equation y equals 0.004 on the interval from 0 to 0.02. Okay, so we're supposed to find every time that graph has a value of 0.004. And I'm not going to say I know exactly where that is, but let's just say that maybe that was here. So they want us to find every time it's that value. Does it make sense? And like I said, I don't know that that's actually where it is, but actually I'm pretty sure it's not. I just saw something, but that's okay. We're trying to find every place where that's true. So what we're going to do is we're going to set our model 0.004 sine of 300 pi x equal to the y value they want this to be, 0.004. And because that's the same as A in our graph, it's actually not there. It's really, let me do this in red. This is where in red where it really happens. It actually happens when we're at the high value, because the middle is 0, and so the high value is 0.004. So that's what we're actually finding. Not what's marked in green, but when does that happen? When does that happen? Etc. Okay? So, solving this equation. Divide both sides by 0.004 to get the trig function all by itself, which gives you 1. And if you think about the unit circle, since sine being 1 is a unit circle answer for a quadrantal, said this a couple of times, but it bears repeating. X, if it's a unit circle, will be cosine theta, because cosine theta being x over r, when r is 1, x over 1 is x. And y will be sine of theta for the same reason. And where on this circle has sine equal to 1? Well, it's where y is 1 on this circle, which is right here. That's where y is 1. 0, 1. And so what angle is that? That's pi over 2. Okay? So that happens when the argument 300 pi x is equal to pi over 2, and anything coterminal with it. So plus 2 pi n. So to solve for x, we're going to divide both sides by 300 pi. Okay. And let's see, that's going to be, pi's cancel, so 1 over 600 plus 1 over 150 n. Since they wanted us to find an approximation of those, I believe. Yeah, it says estimate all solutions until we get to 0.02. So I'm going to type this in the calculator. 1 divided by 600 is approximately, hold on, x is approximately 1 over 600 itself, which is 0.00. I'm going to take this one extra place. It's actually 001 and then 6 repeating, but I think I'm going to do that so that we can kind of see a little bit more information about the number that we've got. Okay? Then add 1 over 150 to get the next answer, which is 0.0083. It's actually 3 repeating. And then do that again, 0.015. Do that again, and that's 0.021 something or other. That's too big. Okay, so that means that our solution set contains just those 3 numbers, 0.0017, 0.0083, and 0.015. That's all the answers between 0 and 0.02. Okay, that ends this lesson. I will see you in class.